Hi everyone. So my name's Chris, and my project was I titled Eclipse Enhancement, a Monte Carlo investigation of brachytherapy dose models. And my supervisors for this were Pejman and Luke. So I just want to give a very brief context on high dose rate brachytherapy that is done here at Charlie's. So a high dose rate brachytherapy is anything that involves a dose rate greater than 12 gray per hour. And unlike low dose rate brachytherapy, it tends to lead to, it can have like worse earlier tissue effects, but better later effects. But it is a lot faster. And here at Charlie's, the source, the radiation source that is used in this is Ir-192. The other thing you can do with a high dose rate is you can do what's called pulse dose rate, where you can mimic a low dose rate by modifying the timing that you would do in order to get a similar low dose rate, and that can lead to a sort of the same early effects as a low dose, as well as the better late effects as well. But it is somewhat slower than HDR because, because the timing's a lot slower. And with a Ir-192 source, you can do both of these things. And the kind of brachytherapy that's done here is surface brachy, which is done by placing a plaque applicator on a patient, and you would have drilled catheters through that, and you can thread the source through that using a remote afterloader. Sorry, there we go. So high dose rate brachy, unlike low dose rate, needs to be done with a remote afterloader because the high doses pose a considerable risk to staff. So it needs to be in a sealed container until it is able to be used. And then the positioning in the patient is very important because you, while the dose rate drop off is quite sharp in brachytherapy, and that's its sort of principal advantage when treating patients, you need to ensure that the position is optimized. And the way that that is done is through inverse treatment planning. But because we have steep dose gradients, the accuracy in order to optimize this needs to be incredibly high. So when you do the dose calculations in order to do inverse treatment planning, you need to ensure that we're getting at least within a sort of a 2% margin of error. And at Charlie's, the brachy treatment planning is done by Eclipse. And this has two different dose calculation models presented. It's the TG43 model and the new one, Acuros BrachyVision. So the TG43 model is, like the name suggests, is based off of the dose calculation protocols that are outlined in the task group number 43 and its updates. And this is simply taking a calculation of the dose rate parameters. So we have the the air coma strength, the dose rate constant, the radial dose function, and the 2D anisotropy function. And this is done by simply having the source placed in an effectively infinite sphere of water, so just a very sort of large radius, usually anything on the order of about 40 centimeters or greater, with the source placed stationary in the center. And then either you can do a Monte Carlo calculation, TLD dosimetry, to generate a table of dose rate parameters. This is based on, so you have the geometry function, which gives you a sort of a grid approximation. And then you feed those tables of parameters into your treatment planning software, and then it can just interpolate that data to calculate the doses that you want. And this is quite a quick thing to do, but it is incredibly simplistic. So it doesn't really account for, it's only really valid for doses to water. It doesn't account for like the heterogeneity of patient tissue, and it doesn't account for patient geometry or any other secondary scatter things. So the other dose calculation model is Acuros BrachyVision, which is a grid-based Boltzmann solver. So this is a discretization of the linear Boltzmann track equation. It's an approximations of that. It works by basically calculating the angular photon fluence for different energies, and it utilizes multi-group approximation, discrete ordinates, and the finite elements method. The finer details of this are quite complex and lie outside of the scope of this talk and my thesis, but while it is slower than TG43, the TG43 model, it is been demonstrated to have a similar accuracy to a Monte Carlo method, although the because it is able to account for scatter effects in more complex scenarios. So the aim of this project was to attempt to assess the accuracy of these dose calculation models in the Eclipse planning system. So I was attempting to build a working computer model of an HDR Brachytherapy GammaMed Plus source, which is the one that we have here at Charlie's. I was then going to use so a Monte Carlo simulation to calculate dose rate parameters as a benchmark to make sure that my simulation was working at all, because I'd never done this before. I've never worked with a simulation, and it's important to make sure that it was working correctly. And then once I was confident that it was, use it to simulate the dose distribution in a series of water phantom tests that were designed by Luke, and compare it with the dose calculation models with the data that Luke also had provided me. So my method for doing this, the initial one is phase one is my benchmarking process. So I was to construct the GammaMed Plus source and then check the dose rate parameters in TOPAS. In order to do this, I needed to measure the photon fluence in a window of sort of a voxel, sort of a rectangular voxel that was of dry air that was positioned 1 meter away from the center of the source axis, like perpendicular to the longitudinal axis of the cylinder. I could then use that to calculate the air curvature strength. Then I would construct a water phantom in which I would be able to measure the dose rate constant, and then also measure the radial dose and 2D anisotropy functions from a similar simulation. Once I had that, I could compare it to existing literature to see if the results I was getting made any sense. Past that, I would attempt to do the same dose comparisons in the 3 different water phantom scenarios and compare these to the dose models. So the 3 scenarios were just a stationary source in a water phantom. Then there was a line of dwell points, so the source is moving, and then a hexagonal grid of that line of dwell points. So there'd be 7 different dwell points that were just like lines of dwell points. Then retrieve the dose calculations and compare them against TOPAS, which is the Monte Carlo code that I ended up using. So TOPAS is an acronym for Tool for Particle Simulation. It's essentially a wrapper for a physics Monte Carlo simulated GANT4, which is a C++ coded physics simulator. Both TOPAS and GANT4 are free and open source. It's a relatively simple and easy to install on a Linux system. And it runs by, you simply generate text files of your TOPAS code. You have to be quite explicit with the parameters that you provided, otherwise it won't run. It's fairly robust at not running when it shouldn't. You can still make mistakes to your simulation setup and it will run, but if you've made some fundamental error, like use the wrong units or something, it won't run at all. And it's a fairly, while it is a fairly rigid system, it is easy to extend with modules if you have any sort of understanding on how to do that work with the GANT4 code. And so over the years, there's been a number of modules attached to it because it was originally a proton therapy tool that had been extended into an external beam, and people have since added brachytherapy. And it came with the photon energy spectra for Ir-192, which was handy for this. So on the right here, we have a table, which is my Monte Carlo summary. This is something that recommendations make in TG186, which is the current sort of guidelines for attempting to validate model-based dose calculation algorithms that are attempting to replace the TG43 model. So my code here, was version 4 of TOPAS, which is also called Open TOPAS, and GANT4 version 11.1.3. For timing, my benchmarking simulations I did with 10 to the 9 histories, and all my other simulations were done with 15 times 10 to the 10 histories. So the source description was the Ir-192 GammaMed Plus. So when you run TOPAS, you have to select the GANT4 physics modules you want to use. I use the G4EM standard.opt4, which is an optimized physics package. It's considered to be quite reliable. There's from the literature I read, it seemed to be acceptable for this sort of work. My variance reduction tool was a track length estimator. I will describe that in more detail in some future slides. So the scored quantities that I was extracting was the dose coma sum, which is related to the track length estimator, and the standard deviation of the dose at each voxel. And I did that so that I could extract a history by history uncertainty method in order to be confident that my model was accurate enough. And then for post-processing, so because I was scoring by the sum of the dose, I would divide that by the number of histories to get the dose rate in terms of per history, and then had further processing in order to convert it into a treatment planning system dose. And then that was visualized with some Python code that I had written up. So just to just give a brief overview of what the Monte Carlo simulation is doing. So Monte Carlo is a numerical method which exploits statistical features of large sets of stochastic data. And so in this case, it's able to approximate a solution to the linear Boltzmann transport equation. So here we have, this is just a kind of a very crude idea of what the thing is doing. So if you consider this grid to be the scoring grid where we care about, the dose that we're calculating, and that thing in the middle is the source with its encapsulation, and with the source, the applicator cable coming out the back. And so every time a history is run, it is generating a single photon random. So it's assigning a random point within the source cylinder. A photon is generated at a random angle with a kinetic energy that is determined by the weighted fraction of energy that can be emitted and then it is emitted, and it will interact with the medium depending on the interaction cross sections, and the dose will be deposited accordingly. The arbitrary and Monte Carlos have a sort of arbitrary accuracy in that you can basically increase the accuracy as large as you like. All you have to do is increase the number of histories, and there's a trade-off between the accuracy and, because it's inversely proportional to the square. The uncertainty is inversely proportional to the square root of the number of histories you use. And so basically the main drawback with Monte Carlo, despite it being extraordinarily accurate and why it's not used clinically for treatment planning, is that it's computationally very expensive. So even with sort of modern computers, it has very slow simulation times. All of my simulations with the equipment I was working with took on the order of about 3 days, at least. And you can see from the diagram now, every time the photon is interacted with the water, it is generating secondary electrons. And every time you generate a history, you also have to generate and track every secondary electron, and this can lead to this can essentially take up about 50% of the runtime at most. And so there are a number of variance reduction techniques that can be used to mitigate this. So a variance reduction technique is just something that allows you to trade off the runtime for accuracy in some way. And so there are TOPAS generally has 2 ways of doing this. You have the Russian roulette and particle splitting, and these are sort of built in. So one is you basically have a threshold value somewhere between 0 and 1. Every time the photon undergoes an interaction, a random number is assigned to it. If that random number lies over the threshold or not, it will make a decision about whether to simulate that secondary particle. And so you can use that to limit the number of secondary particles. The other one is known as particle splitting, which is somewhat similar, except instead you can sort of, when you generate the secondary particle, you can estimate the effective range it has, and then you basically change, you use a random number generator to rescale that range in various ways and then in various directions, so you can get a sort of an approximation for the dose, so you don't need to run as many histories. And so these are all well and good, but the problem is that TOPAS, because it's not really designed initially for brachytherapy, it doesn't really work with volume source emissions, at least not that I could tell. It really requires a sort of a beam sort of source to really take full advantage of. So what is generally used instead, which is something that's been sort of attached, is something that's somewhat called a Kermer approximation technique. And so what that is rather than scoring by the dose, we score by collision Kermer. And we're able to do that with this Ir-192 source. So typically with a Kermer approximation is that you only consider generating secondary particles that are above a certain energy threshold. But for the energies of an Ir-192 source, the sort of effective range of any secondary electron is not going to be very large. It's going to be some very small fraction of a millimeter. And so what we can do is use the track length estimator variance reduction method, which is where we just don't generate any electrons at all, secondary electrons at all, and we just consider that the dose has been deposited locally every time the photon has interacted with the water. And this is an approximation which has been shown to hold very well, as long as you are not anywhere where charge particle equilibrium does not hold. So this is basically within the source itself and within about 2 millimeters from the source surface, where you can still calculate the dose, but the uncertainty goes up by a factor of 10. And yes, so this is instead, you'll be basically scoring by Kerma instead of dose. So to build the source, I needed to construct the source itself in TOPAS. So in order to do that, I got some Luke provided me with some consensus data on the and which contained the dimensions of that source. So there were two ways I did this. I originally made an STL file of the source dimensions in Autodesk Fusion 360, and I just made a nice image of that on the left there. And then I imported the STL files into TOPAS, and that worked fine, but there was some history loss due to some mesh collisions. And because this thing is relatively simple, I was able to just use the inbuilt Giant for geometry to generate it from half lengths, and that was a lot simpler. And the only thing you need to do with whenever you're creating any geometry in TOPAS is you need to ensure that you have included any material or and then to do that, you just need to give it the molecular fractions of any elements that it's composed of and the density of it. So I was able to obtain that information online and use that to fully create the source. So then I was able to attempt to generate the Kerma strength. So in order to do that, I used the energy range, the photon spectrum that was within TOPAS, which was, I believe, from the National Nuclear Data Center. I then obtained some NIST data for the mass absorption attenuation coefficients for dry air near sea level, and the energy ranges associated with that. And then I used a linear interpolation to work out the mass absorption attenuation coefficients over the energy range that I needed. Once that, I was then able to construct the Kerma parameter. So this is just a 3 meter cubed a vacuum with the source in the center, and then there's a 10 square centimeter by half a centimeter dry air voxel 1 meter from the source. And I ran this for 10 to the 9 histories to get the photon fluence. I then combined that as a sum with the mass attenuation and the energy range. And then this needs to be scaled by the average number of photons emitted, so the photon intensity, which is on the order of about 2.003. And then this also, in order to scale this, it needs to be multiplied by 1 meter, which is just 1 in this case, to get the Kerma strength. Then to calculate the dose rate constant, I simulated a 40.1 centimeter cube of water, simulated 10 to the 9 histories again. So in this case, there was just a single millimeter voxel at the reference point, which for a high dose rate source is 1 centimeter perpendicular from the center of the source axis. And then, and it's 1 centimeter, and the angle there, it's just pi on 2, and use that to calculate the dose, the track length estimator to calculate the dose Kerma. So that gave me the dose rate. Intensity was the same as it was in the previous, and then I divided that by the Kerma strength to calculate the dose rate constant. And so you can see that is I got a Kerma strength of 0.0986 plus or minus 3 U per megabecquerel, and that seems to agree quite closely with the papers that reported this. It's not often reported, I found, in a lot of papers. And the dose rate constant seemed to agree quite closely. It agreed with all within 2 standard deviations, and most within 1 standard deviation. And I think any differences there, I think, mainly come from differences in the Monte Carlo code that was used, and possibly variations in the experimental setup and the number of histories that were used. So once I had that, I needed to get the radial dose function and the 2D anisotropy function. So the first thing was to use a 40.1 cubic centimeter cube of water simulated with 10 to the 9 histories. The scoring grid again, in this case was 20.1 centimeter squared. The 0.1 is just there so that I have a center voxel. It just made calculations a lot easier. And using a voxel resolution of 1 millimeter cubed, and then placing that scoring grid in sort of the midplane of the XZ axis. Once done that, I used the geometry function, grid approximation from TG43 to calculate the geometry function, and using this beta I found, and then calculated the geometry function as the dose rate over the dose rate at the reference point times the geometry function at the reference point divided by the geometry function. And then also used a spline fit to find the like a fifth order polynomial spline fit to work out the polynomial approximation of this, which is apparently the case in some treatment planning systems. So that was relatively easy to get as well. And so I plotted all this on a graph and compared it against some papers. And I found that within 2 standard deviations, it seems to agree relatively closely. The black line is the spline fit I made. There are a couple of strange deviations there, and I think that it's partly because my thing was only because I could only get the radial dose to be out to about 10 centimeters, whereas most things were measuring out to about 20 or 30. But it seemed consistent enough, and also I think the number of histories I chose was fairly low for this, so I think that probably would have been had more of a tighter spread if I'd used more histories. So then the 2D anisotropy function, all I needed to do was take the data I had, and you just scale the dose rate relative for the fixed for the dose rate for fixed at the reference angle, and plotted that. I believe I could have gotten more data points if I had either used a finer scoring grid or possibly just had more of used some thresholds for my angles. But based on the data I got, I thought it seemed to agree fairly well. The further out it gets, the more uncertain it seems to get. But I think partly that may have just been the spline fit I used to make the curve itself. I think the data's not too bad. And again, I think that's just because the number of histories I'm using it's probably slightly less than I should have, but I think it's consistent enough that I was confident it was working properly. So then moving on to the water phantom tests, we had a 30 centimeter cube of water for all the tests. So the stationary scenario had a half millimeter voxel resolution, and it consisted of a singular dwelling point that was just, the treatment time was over 20 seconds. After that, I decreased the voxel resolution to 1 millimeter because it would just mean I could do the calculations a bit faster because the calculations were on the order of days. So the line scenario is, as you can see in the top image, it's just like just each dwell points are 1 centimeter apart. There are 7 of them. Sorry, there are 10 of them. And each dwell time is 7 seconds each. And then for the hex grid, we have each line of dwell points is like 4 by 9 centimeters apart in a hexagonal shape. And same same resolution as the line scenario, and now there are 70 dwell points, and each is 5-second dwell times. So the source cable in this case I simulated to be about 14 centimeters, which is touching more or less the edge
Chris,
of the.
Sorry to interrupt. We're going to have to cut it off in 5 minutes because we're just a bit over time. That's been 30 minutes. Yeah.
Oh, I'm sorry about that.
That's all right.
I guess I'll try to be very quick then. To get the idea there, yeah, so to do the dose calculation, we worked out the dose rate parameters from these dose calculations. It would take about 4 days to do the simulations. So looking at my initial results, these are just the relative dose plots of the two different treatment planning systems against TOPAS. TG43 seems a bit peculiar, but it's likely because it's very much an approximation. And we can see this is looking at the line source and the grid source. But so the key results here is that, yeah, TG43 seems to be generating a, like it seems to be overdosing, giving like a local dose where we're comparing the Monte Carlo dose to the treatment planning system divided by the treatment planning system. So looking at local voxels, it's definitely disagreeing with Monte Carlo more than Acuros is, and there's more of an overdose. And that's a sort of a global variance where the spread is tighter, but still more so than not as much as Acuros. And so just going by my main results here, basically the take home is that the local dose for Acuros is more in agreement with Monte Carlo pretty much in literally every single test I did compared to TG43. And so this is just sort of local agreement. The behavior of both seems to agree if we're looking at like distances relatively close to the source, sort of in like clinical distances, but the performance is about equivalent, I think. So yeah, so my conclusion is I successfully built a Ir-192 GammaMed source, simulated the dose rate parameters, compared the three results with the Eclipse, and Acuros appears to agree with Monte Carlo equally or better than TG43 with the experiments I performed. There's some further work to be done, though. We want to examine the dose performance at material boundaries, different sized air gaps, different sized bone regions, import CT DICOM files into TOPAS, compare with clinical treatment plan with Eclipse data, and then you could do some dosimetry comparisons as well. So I just want to thank my supervisor Pejman and Luke for the data and advice and all the help they gave. Francisco Berman Marullo from Laval University, who his tutorials and emails were very helpful. Joseph Pearl and everyone on the TOPAS forums. Nathaniel Gavin and Ash Leisha for all of their help and advice. Everyone in the medical research physics group, and all of my colleagues for the 2023 to 24 medical physics master's cohort. Thank you.
Thanks very much, Chris. Great presentation there. Did we have any questions for Chris?
Rashid.
Yes, thanks, Chris. This was great. I'm actually quite surprised that you can do all of that in such a short time and dig deep into all the physics. You've done a great job. I just have two small questions for you. One is, have you used any cutoff energy for your simulations?
The cutoff energies? Only, no. So the cutoff energies were purely just, yeah, so whatever was in the TG, the TOPAS energy range.
Right. So it didn't give you give you permission to choose your cutoff energy, right?
You can choose if you want.
Okay. Because I was just thinking, because it took you such a long time, using a cutoff energy could have helped speeding up the process. And just out of interest, were you using GPU or CPU?
CPU.
CPU. Okay, that's another thing that slowed you down. And just one CPU, or was it like a cluster?
It was a cluster, so I used as many
Cluster.
cores as I could with every the 3 CPUs I was using for every simulation I was doing.
Right. Okay. Thank you very much. Well done.
You're welcome. Thank you.
Thanks, Mashid. Any other questions for Chris? Brilliant. All good to go. Thanks, Chris. Right.